Welcome students. In today's class, we will look at the least mean square algorithm. Under that, the statistical analysis of the LMS algorithm considering the small learning rate parameter. Now, LMS are the least mean square algorithm used to adjust the weights in Annealing. What is Annealing? Annealing is adaptive linear neuron or adaptive linear element. And for understanding this LMS algorithm, for adaptive linear neuron, we will consider a perceptron with two inputs x1, x2, and a bias input with bias as stagnant, that is stagnant in the sense held at +1, and weight for the bias is W0, W1, and W2. And we know in the perceptron, we do the summation weight with the input vector. Now, this is the predicted output what we are going to get. That is y is equal to summation of wi and xi. That is here I is ranging from 0 to 2. But when we take this input parameters, that is x1 and x2, that will be considered as a training parameters. And now for training parameters, if this x1 and x2 are the features, and they will be having some desired output. That is, if this is the input, what is the output that we are expecting? That is the actual output will be there. But now we are passing to this perceptron the input and we are asking it to do the prediction. But now actual, predicted output is summation of wi xi, that we will call it as y. Error will be obviously the difference between the desired and the y-axis. That is, the error is going to get generated. Now, when the error gets generated, we have to think about like how we can change this weights so that we can get the error with minimum. Like we cannot tell we will get zero error actually, but we have to look for minimizing the error. That is, in the Annealing or the adaptive linear element, we are going to generate, that is, we are going to find the error by computing the difference between the desired output and then the actual, that is, predicted output. Now, if we got some error, the question is, like then we have to change this weight values W0, W1 and W2 to what values? Because we start with some random values, but we have to learn over a period like what is the best values we can use for this one so that the error will get minimized. One algorithm which we can use to update this weights is the LMS algorithm, that is least mean square algorithm. That is, in this class we will look at how this LMS algorithm is going to work and which is going to help us to update the weights. Now for this Annealing, we'll consider the input as x of n. That is x of n when we take, it is at the time, n is for the timestamp or the nth iteration. That is the meaning. At the nth iteration, what is the input? It is an input vector comprising the inputs, that is x1, x2 up to xm. And similarly, the weight vectors, that is w1 and w2 and then wm, and desired output for that particular input feature vector, and then the output what we are going to predict, that is y of n. Y of n is equal to, that is x transpose and w of n. It is to make the matrix as 1 cross n and then n cross 1 so that we will get the output as 1, because y will be one single number when we do the multiplication of these two matrices. That why we are going to subtract with the desired output. What we know the desired output, but our task is we have to make this y equivalent to or almost near to the desired output by finding the best weight values for W1, W2 up to Wm in this case. What are the best values we can give for this particular numbers so that our error is going to get minimized. Now in this equation, that is d of n minus y of n, and y of n we know x transpose of n and wn. Now our task is to minimize this error. We will take the squared error because it is a difference, therefore we have to take the squared error. And now we will multiply the squared error with the of, because next we have to find the rate of change of the error with respect to the rate of change of the weights. Therefore, to simplify the differentiation, we will multiply by 1 by 2. That why it is called least mean square error. In this is we are taking the square of the error. That's why it is called as a least mean square error, least mean square algorithm, or the LMS algorithm. Now, in the previous slide, we got this equation, that is E of n is 1 by 2 e square within brackets n. Now we'll differentiate this term with respect to the weight vector w. That is, now when we differentiate this of and then the 2 term will get cancelled out, and we'll get E of n and then dou E of n by dou w. That is differentiation with respect to weight. And we know the E of n term, that is the error term, is d of n minus x of n and wn. And now in this one, we will substitute this particular value, that is what we got actually, that is dou E of n divided by w is minus x of n. Sorry, 1 minute. Sorry. This one, this differentiation is there, that is fine. We are differentiating this small e now, that is dou E of n by dou w. That is, this is a constant, because one number, desired output, a constant. Therefore, this gets cancelled out. And differentiation of the X transpose matrix is going to give the matrix itself. Therefore, we will get X of n, and negative term is a, we will get the negative term. And this will get cancelled out because we are differentiating with respect to the W. That is differentiation of small e of n divided by the differentiation of w, the dou of w, we are going to get minus x of n. Now this term, what we got, we will substitute back in this one. That is this term actually. That is for the capital E actually. That is, now when we substitute, we are going to get now for the capital E of n as minus x of n and then the E of n. That is, this is what the term what we got actually finally. Now we will follow the general steepest descent update actually with respect to the update of the weight. We have seen this also in the convergence theorem, because in the perceptrons convergence theorem, I said that is update of the weight is w of n plus 1 is equal to w of n plus learning rate multiplied by x of n we took. But now we have to take the error into the consideration. Therefore, now next update of the weight, that is w of n plus 1 will be w of n minus, because this term what we got is from here actually, that is this particular term, and then this particular the error term differentiation. That is, this learning rate why is required is with what because I cannot take the entire term error term value as an subtraction value for the w of n. We will take the portion of that particular term, that is how much have to update with respect to this one. Therefore, we will multiply by this learning rate value. That is, learning rate is we as an users, when we are training the model, we can fix this value. That is, this is only to tell us like with what portion of value I should use this particular term, that is minus x of n and e of n. That is, now finally from the LMS algorithm, what we are getting is w, that is update of the weight. Next update of the weight, w of n plus 1 is equal to w of n minus learning rate and then minus x of n and then e of n. This is what the term we are going to get. Now, what is the summary of the LMS algorithm? For the LMS algorithm, input vector is given by the SIGA, that is the input signals term vector x of n. Desired responses are given by d of n, and user selected learning rate parameter. And then we can start the initial weight vectors with a random, or we can start with a 0. And then we have to compute for n number of iterations. And in each iteration, we will find the error by computing the difference between the desired output and then the predicted output. And then after that, the next update of the weight is going to be taken. I think this was a minus here actually, because that is what we, no, sorry, what one observation we have to do. That is in the perceptron convergence theorem, that is when we are going in the opposite direction, our W of n plus 1 and W of n will be W, that is W of n plus 1 is equal to W of n minus of n of x of n will be there. That is, your minus term is there because we are going in the other direction and we want to bring it down. Therefore, negative term will be there. Therefore, this minus with minus is going to become plus. Okay. Therefore, now final LMS algorithm now will be, that is update of the weight is W of n plus 1 is equal to W of n plus learning rate and then multiplied with the input vector and then the error vector. That is what we are trying to understand here is update of the weight will depend on the learning rate, input parameter, and how much of error we have got in the current iteration. Depending on that, we are going to update the weight. Now the next question is, when we keep, that is this n will be keep going on, like whether this algorithm will converge. Converge in the sense, can I get some stable values of the weight vectors W actually, so that the whatever we are going to get, the predicted output is going to minimize the error. That is the question we are looking at. That is, LMS algorithm is taking the steps to update the weights. But is there any convergence? That is, it will try to help us to find a design that is a stable or optimized weights, so that the algorithm will converge, so that we will get the output. That is, we can predict the output by using the weights, so that the error is going to be minimized. That is the question. For that one, we have to do the statistical analysis of the LMS. That is, statistical analysis of the LMS will look, that is, it will tell, that is, statistical analysis tells us whether the random learning process is stable and convergent and accurate and average. That is, question is whether it will converge finally. That's a question. Because why we are asking this question here is in the LMS, because x of n is an input. It is a random input, whether it is an image or whether it is a CSV file or any data. It is a random input which is drawn from the input samples. And then desired output, that is, for that input we are having some desired output. Output is there, that is it is there, but it is also drawn from the samples. And E of n is the error what we are getting, because we are subtracting between the desired and the actual. And the weight what we update, because the weight updation is by the equation, it is also random. This means that weight vector is also random quantity. We cannot predict exactly what weight will be at time n equal to 100, because it depends on the random data sequence. As we keep running the algorithm from n equal to 1 up to this particular point, at the 100th iteration, I can tell what is the weight vector. But I'll get some weight vector. But this particular, it will tell that the algorithm is converging. Algorithm is converging in the sense I'm going to get a minimum error. But because I would have started with a random weight, my error would be very higher at the starting. But as I keep going on, whether my error will be will get minimized as we keep updating our weights. That is a question mark. That is, this is the statistical behavior of the LM. That is, in the LMS algorithm, why we have to do the statistical analysis is, we are having everything as a random, whether it is an input or whether it is a desired or whether it is an error or whether it is a weight. When we use this algorithm to update the weights, whether finally the algorithm will give the will converge in the sense, can I get a weight where the error is going to get minimized? That is a question mark what we are asking. Now, when analyzing the statistical behavior of the LMS algorithm, the weight update equation becomes a stochastic difference equation. Stochastic difference equation in the sense, that is what we did. It is W of n then and W of n, and then learning rate, and then X of n, and then the error h. Everything is random, therefore it is stochastic because it depends on the random input. To make the analysis mathematically tractable, three key assumptions are made. That is, we are doing statistical analysis of the algorithm to get the answer whether the algorithm will converge. Now, to show that this LMS algorithm will converge, we are going to make three assumptions. Assumption 1, assumption 2, and then assumption 3. Using these assumptions, we can tell that we can get, that is, we can show that the LMS algorithm will converge. What is the first assumption? That is, learning rate is small. That is what the first assumption. That is, learning rate parameter we have to take small. In LMS, the weight update depends on the random input samples. If n is small, the weights change slowly. That is, if we start with a too high learning rate, weights will get changed, but it will get changed too fast, and we may miss that particular optimum weights what we needed. Slow changes in the weights allow the random fluctuations to average out. This makes the algorithm behavior approximation like a deterministic system. That is, even if we start with a stochastic nature, the algorithm will finally behave, or the system will behave like an deterministic. First assumption we are going to do is that is a learning rate should be very small. Second assumption, the estimation error is wide and uncorrelated with the input. We are calculating the error E of n equal to D of n minus desired output with respect to the predicted output Y of n. But this error, we are assuming it is wide and uncorrelated. What is the meaning of the error is wide? That is, error is wide means no correlation between different time instances. That is, here, say E O of n and E O of m. It is a two different errors at two different time steps. And when we find the expectation or the correlation, it is 0. It indicates that is two different errors, errors at two different instances are not having a correlation. And also, past errors don't fluctuate, future errors. That is, past errors are not going to influence the future errors. Because if I got some error today at 0.5, you're not telling like of the next nth plus 1 iteration, this is going to affect. In case if n equal to m also, the error difference between the two terms once again will be some that is, there will be some error. We cannot tell there is no negligible error is there, but there will be an error. That is, error is wide means no correlation between different time instances. That is the meaning. Next assumption what we made is what that is uncorrelated with the input. What does uncorrelated with the input tells us? The input signal and the error have a zero correlation. There is no correlation between the input signal and the error. That is, knowing the input gives no information about the residual error. That if I know the input x of n, we cannot tell actually until we multiply by the weight vector and subtract with the that is the desired output. We cannot tell the error. We cannot tell. Input will try to tell me what may be the error, that we cannot tell. That is, here expectation of x of n with error term is not equal to 0. That's the meaning. Now, third assumption is the input vector and the desired response are jointly Gaussian. That is, input vector x of n and desired response are assumed to follow the Gaussian distribution. That should be there. Because why this assumption is needed is Gaussian processes are completely characterized by the mean and then the covariance. Because if I take Gaussian distribution, it can be categorized by the mean and the covariance. So that some pattern is there for the input and then the response. Therefore, second order statistics like correlation matrices fully describe the system. This makes the mathematical expectation easier to compute. Because when x of n input is there and d of n is there, We tell random, but at least it should follow some pattern, because if it follows some pattern, then only we can make some mathematical computations easier, or we can get some expectation. Therefore, what we are telling, this x of n and d of n are going to follow Gaussian distribution, because that will enable the closed form analysis of convergence and the stability. That is, it will help us, that is, algorithm will converge and it will get stabilized. Now, what we have done is we looked at the LMS algorithm. In the LMS algorithm, the weight update was W of n plus 1 is equal to W of n learning rate and then x of n multiplied with the error term. Now, this updation is random. Therefore, can I get weight update so that I will get a, that is, convergence will happen with some stable weights to get the desired output, and then the predicted output equal with the minimum error. We will not go and show the convergence of the LMS algorithm, but only we have understood that that is, this assumptions will simplify the statistical analysis of the LMS. Statistical analysis of the LMS algorithm asks the question whether the LMS algorithm will converge. That is to say that LMS algorithm will converge. We have done three assumptions. If we make these three assumptions, that is, first assumption is learning rate is small. Second assumption is estimation error is wide and uncorrelated with the input. And the third assumption is input vector and the desired response are jointly Gaussian distribution. If these three assumptions are made, and then we can show that statistical, that is, LMS algorithm will converge. But we will not proceed with showing the convergence actually, but only we have made this assumptions. That is, finally summarizing, if the learning rate is small, the error is uncorrelated with the input, and signals are well behaved statistically, that is, one example is the Gaussian distribution, then LMS behaves like a stable linear system and converges on the average to optimal weight. That is, converges an average to an optimal weight so that the error will be minimal. That is only thing we are looking at this particular uh, topic with respect to the LMS. Now, next we'll proceed with the learning rate annealing, because we took in the LMS algorithm this learning rate. What are the different ways I can update? That is, what are the different ways I can start this value? What are the different effects that will have with different ways of assigning the values for the learning rate? That is the question we are asking. Learning rate annealing is essentially a strategy to reduce the learning rate as the training progress, allowing the model to make larger updates early on when it is still far from the optimal. That is, when we start learning, we are far away because we start with the inputs weights as 0. We may have to get the weights with, say, the value as 0.1 or 0.2 something. It is far away. At the starting, actually, how should I progress this particular weights actually, and how should I go? As I keep updating this weights, I may be very closer to my optimal values or the results. At that time, that is more refined updates as it gets closer to the solution. At the time, updations should be very slow. That's the question. That is, to understand the learning rate annealing, what it asks, it says is, it is a way of shrinking the learning rate over time to help model settle into a most optimal position. What is the best way we can start with the n value, and what way we have to keep increasing or updating this one so that we will get the optimal solution. That is, when we first start training a neural network model, the model needs a bigger learning rate to make bold moves, explore the landscape, and find promising areas of improvement. But as the training progresses, the model needs to slow down. That is, as it keeps progressing, we have to make the model to slow down little bit. that is taking smaller but more careful steps to fine tune its understanding. That is, learning rate annealing schedule is asking a question: how can we keep updating the learning rate parameter so that at the starting we should take little bigger steps, but as the training progress and the model is getting stabilized, then our updates should be very less. Then how we can use this learning rate parameter is the question mark. Now, to understand this learning rate updation, we have a graph here. I'll explain this graph step by step, but if we understand this graph, then we'll understand how the learning rate has to be updated during the training process of the neural network. In this graph, the vertical axis, that is this one, is a learning rate, that is n of nth. That is nth is a nth iteration at that particular distance. Horizontal axis, this one, is the iteration number. The iteration number we will take in the logarithm scale, because if there is no logarithm scale, like what we are getting at the 10th iteration and then 20th iteration, 10, that is, it keeps going linearly. But when we go with the log of scale, it will be 10, 100, and then 1000, and then we will keep going. Because as we progress in the epochs in the training process of the algorithm, we have to look at the visualization with the larger extents. Starting, I should observe how it is progressing, and then I can make a bigger steps and then look at how it is progressing. Therefore, the x-axis is a log scale. That means early iterations are spread out, because in the log scale, if it is 10, 100, and 1000, starting it is being spread out. It is small. Later, the iterations are compressed. That is, we keep increasing in the log scale. This makes the decay patterns easier to compare visually. That's why we are using the x-axis as a log scale, which will show the visualization in terms of 10, 100, 1000, and 10,000. Now we'll understand this graph with part by part. We'll assume that with the learning rate as 0.1. We will compare three cases. One is the constant LMS, or the constant learning rate, and the other is stochastic approximation of the learning rate, and the other is search then converge. That is, what is the effect of this learning rate under these three cases? Constant learning rate, stochastic approximation is a learning rate is equal to C by N. C is a constant, N is iteration number. And then state then converge is being given by N of N equal to starting learning rate, what we have used, N naught divided by 1 plus N by tau. Tau is also user defined constant. And N iterations will be increased in terms of log scale, that is 1, 10, 100, and then 1000. First, we will look at the first case. The first case, that is a constant case, where learning rate is same for all iterations, that is 0.1. If n is 1, the learning rate is 0.1. If the iteration number 10, the learning rate is 0.1. At the 100th iteration also, the learning rate is 0.1. That is what we are observing here in the blue line here. That is, if we consider the case of a constant learning rate, that is, as we progress with the iterations, the learning rate is not changing. Therefore, it goes horizontally, the same thing. That's the meaning. As we keep going in the iterations, the same learning rate. That is, if I started with 0.1, at the 10th iteration, it is 0.1. At the 100th iteration is 0.1. It is the same thing. That's what the blue line indicates. That is the first case. Now we will look at the second case, stochastic approximation. For the stochastic approximation, N of N equal to C by N. C is some user defined constant. We'll assume or consider it as 0.1. When N is equal to 1, it is what? 0.1 divided by 1, we will get the same. But when N equal to 10, it is 0.1 divided by 10. Therefore, it becomes 0.01. Next, at the 100, it will be 0.1 divided by 100. That is, what we are trying to tell is, when we reach the 10th iteration, my learning rate will change from 0.1 to 0.01. Similarly, when I go to the 100th iteration, my learning rate will change from 0.01 to 0.001. When we do like this, now you can observe here actually, that is, as the iterations go in the horizontal direction here, how the learning rates are going. That is, learning rates are going very steeply actually. It is getting decayed actually. That is, very fast decay is happening, because at 100, n equal to 100, already 0.001. At n equal to 1000, almost 0, because it is 0.0001. This is the steep straight line in the figure. That is, when we assume for the learning rate a stochastic approximation, that is, there will be a fast decay in the learning rate and it goes steeply. That is the observation which we are making. Next is search and then converge. The search then converge learning rate updation is by n of n equal to n naught divided by 1 plus n by tau. But tau is also a constant. We'll assume tau is equal to 100 and n naught equal to 0.1. That is, at n equal to 1, what is the value I'll be getting? 0.1 divided by 1 plus 0.01, because this term is n value was 1 and then divided by 100. Therefore, it becomes 0.01, which is going to get the value 0.099. And then similarly, at n equal to 10, and now when we substitute in search then converge formula, we will get the value that is 0.091. That is, you observe this line which is going like in a curve here, that is search then converge schedule. We will start with tau some value, but convergence will go, that is, starting, it is not going to change drastically. We are searching for the optimal weights actually in this period, because we are in a learning period at that time. But when n naught goes beyond tau, the convergence, in the sense, it n naught will converge steeply. That is going to happen, because you can observe here, that is this this table I'll explain. This is search and then converge. This is n 1, 10, 100 and 1000. For search then converge, you can observe here, initially it is 0.09, after that 0.09. That is, change is very small, but after over a period the change becomes too large and then it becomes too small actually. This if when you observe 0.05 and it goes to 0.009. That is, what we are trying to understand here is, in search then converge, when n is less than tau, that is, learning rate is almost constant. That is, this phase. This is what we are telling. That is, n is approximately equal to constant. That is what we are saying. And the fast learning, that is, we are looking to update the weights and learn in a fast manner. But when n takes the value greater than tau, that is this, beyond this one, learning rate decreases. It keeps going on, because we have seen now from 0.05 it goes to 0.00, that is 009. That is, n decreases and the fine tuning may happen to the model. That is, three cases for the learning rate annealing. One is the constant LMS, and the other is the stochastic approximation, and the other is the search then convergence. That is, this all this three, this thing you can observe here. If it is a constant, there is no change in the learning rate, but if it is a stochastic, then slowly, that is, this is the stochastic, and then search and converge is this one, and for the constant, this blue line. That is, in stochastic approximation, the learning rate decreases continuously from beginning. The line is going like this in the stochastic approximation. In search then converge, the learning rate stays large initially, because here this curve, when we observe, it is stable at the starting. That is learning rate, sorry, in search then convert, the learning rate stays large initially to search quickly and then decreases to ensure a stable convergence. That is the mean.